Good morning and welcome to Science on Saturday. I'm Joanna Albala. I am the manager of the Science Education Program at Lawrence Livermore National Lab, and I'd like to welcome you. Science on Saturday is brought to you in collaboration with a partnership with the Livermore Valley Joint Unified School District, and it's my honor today to introduce Chuck Rogie, who's a member of their board, to introduce our speakers for the presentation this morning. Thank you. Chuck?
Good morning. Who's here from out of town? Raise your hand. Great to see you. Well, welcome to Livermore's Bankhead Theater, and thank you for coming to the 21st year of Science on Saturday presentations. This is the first of 4 presentations created by the scientists from Lawrence Livermore National Laboratory and local science educators. Our topic today is the Shale Gas Revolution. Only 5 years ago, the world's supply of oil appeared to be peaking, and conventional gas production declined in the United States. Today, America's shale gas revolution is having a radical impact on the global economy. Today, Dr. Roger Aines and science teacher Dean Reese will address the technology, processes, and impact of extracting new oil and gas from vast shale deposits in the United States. Dean Reese is the chairperson of the science department of Tracy High School. Dean is also a faculty scholar for the Lawrence Livermore National Laboratory's education program, instructing the Computer Simulation Teacher Research Academy. Many of you will recognize Dean from past Science on Saturday presentations. Dr. Roger Aines is a member of the Energy and Environment Directorate at Lawrence Livermore National Laboratory, where he leads the Geochemistry group. Roger's career has involved a close coupling of scientific research, engineering, field demonstration, and assessment of future development needs for technology. He holds 15 patents in the area of in situ degradation of organic chemicals through heating, simulation of steam-driven underground processes in heterogeneous media, and the mechanisms of thermally assisted remediation. Please welcome Roger and Dean.
Hi, I'm Roger Aines from Lawrence Livermore National Laboratory.
And I'm Dean Reese from Tracy High School.
And it's our pleasure today to talk to you about America's energy system, in particular, the changes that have happened in that energy system just since you were in the 3rd grade. When we say energy system, what are we talking about? Well, today we're going to talk about the energy that you use in your homes and the energy that you use in cars. We're going to skip over industry because we're trying to personalize it to just what do we do here in the room? What kind of energy do we use? Where does that energy come from? Well, oil, we know, comes out of the ground and then we refine it in refineries. Electricity, which is the major energy that we use in our homes, comes from wind and solar. As you'll hear next week if you come to talk, you'll hear about wind. And a lot of it comes from big power plants. Many of those around the country are fueled by coal. And we're going to talk about how that's changing today. And those are now being fueled by natural gas. So let's think about energy and power. What do these things mean? What are the kind of units? How much energy do we really use? Dean, could you give us a light? A little pen light that Dean has is 1 watt. Turns out to be that's a very convenient unit of energy. And if he leaves it on for an hour, he'll use 1 watt-hour of energy. That's about the stored energy that's in a AAA battery. Good way to think about that. Many of you are carrying a cell phone in your pocket that has about 5 watt-hours of energy stored in it. But we want to think about how much energy we use on a larger scale. What about the energy that we use in our houses? Could we have a big light on, Dean? All right. That's 1,000 watts, 1 kilowatt. And that's about the amount of energy that we all use all the time. On average, we're using 1 kilowatt of energy when we're at home in our houses. In California, we use less energy, less electricity than any other state. We're number 1, yes. And that's because we're very efficient in the energy that we use. That 1,000 watts is about how much we all use on average, and the rest of the country uses up to as much as 40% more than that, 1,400 watts. If we use it for an hour, that turns into a kilowatt hour, and that electricity in California costs us about 15 cents. So, Dean, this difference between energy and power is a little confusing to me. Can you help us understand that?
Absolutely. So I just remember being, actually I remember getting my first energy bill when I actually had to start paying for my energy. And I looked at that bill, and a unit was there, a kilowatt hour, and I was completely confused about what a kilowatt hour meant. And I'm sure a lot of people can kind of think about that and say, what does that even mean? It seems like a really confusing unit. So kind of going back to the flashlight, a AAA battery, here we go, AAA battery that's powering this pen light, this puts out a watt of power, and that battery can basically hold that watt of power, that light coming out of the flashlight for 1 hour. So that's why they call it a watt hour. So that kind of makes sense, right? So again, if you're using a watt of power for 1 hour, you've just used a watt hour. And the AAA battery can store 1 watt hour of energy. Power is like energy being used, okay? So the energy that from this spotlight here, that's a kilowatt. Not 1 watt, like the energy coming out of this flashlight, but a kilowatt. Okay, and so that's a much bigger unit of energy, or rather, a much bigger unit of power. And if you used a kilowatt for an entire hour, that would be a kilowatt hour. And that's what PG&E, that's the unit of energy that PG&E will bill us with. And basically, we're looking at how much total energy was used throughout the day.
Thanks, Dean. So that's what we use when we use electricity. But of course, the other major use for us is transportation. And that gallon of gasoline that you see there is equivalent to 33 kilowatt hours. So that gallon of gasoline, if we turned it into electricity, would run that spotlight that was on Dean for a day and a half. That's why we use gasoline to run our cars. It's incredibly concentrated energy. So that amount of gasoline, if you rode to school in that old red truck, would take you about 15 miles. Today, though, in a nice new hybrid car, it'll take you about 45 miles. Much more efficient. Same amount of energy expended, but you get much more value out of it. So let's take a look at how we use energy, where we get our energy from in California. We just looked at gasoline and electricity. Where do those come from? We're going to see a lot of other things up here. You're going to see biomass. That's pretty, what's that? Those are like the walnut shells out in the Central Valley that we burn, and we actually make electricity out of those. That's biomass energy. Hydroelectric power from the dams up in the Sierras. Jet fuel, motor gasoline. Coal, right at the very top, it's a very small bar. We don't get much energy from California from coal that we burn in the state of California. The thing we have to be careful of is the very bottom line down there that says imported electricity. That's electricity we buy from Utah and Nevada and other places where they do use coal to make electricity. So we're, in fact, using a fair amount of coal for the electricity that we use. But the big number on there is natural gas. Great majority of our energy and the great majority of our electricity come from natural gas in California today. And that's good because natural gas is a very clean fuel. And we'll talk about an example of a new natural gas-fired power plant that probably all of you have seen without realizing what it was. This is just off I-5, out by Lodi. You remember where those ponds are out in between Stockton and Sacramento. And I'm sorry, it's on the way to Stockton. I'm going to get myself in trouble with the people from Stockton here, which includes the moderator of the program. This power plant runs on a thing called a turbine. What's a turbine? It's a jet engine that you fire with natural gas, and you see that in the blow-up. And if you look on the right side of that, the left side of that blow-up, you'll see that there's a guy standing there. It's a giant jet engine. It's actually bigger than a jet engine in an airplane. But you burn natural gas, it spins that turbine, and that spinning motion makes electricity. But you see from the blow-up that that's the tiniest part of the plant. Turns out that we also want to use that heat that comes from the natural gas, in addition to the motion that comes from it. We use the heat and use that heat to make steam, and the whole rest of the plant is used to make steam that we run through another turbine and makes even more electricity. This turns this into one of the most efficient power plants in the world. We're getting more electricity out of this natural gas than any other kind of power plant. And utilities love this kind of power plant because it's clean. You've all seen it without even knowing what it was. You didn't realize that was a power plant. And when it runs, it doesn't make a bunch of smoke and it doesn't pollute our air. So we all like that. Well, why don't we use more of this? Because the natural gas wasn't available in the past. Today, it's available, And that's happened just since you were in the third grade. This is a giant change, and it's a change that's going to be present for the rest of your lives. This power plant makes electricity, makes about 300 megawatts of electricity. And Dean, I'm getting confused again. Can you help us with the megawatts thing?
So, scientists like to use units like megawatt or gigawatt or kilogram. And, it's a useful way for scientists to basically represent really large numbers and be able to say them without having to go into the billions, trillions, and quadrillions. You can just basically use metric prefixes and exponents to represent these really large numbers. Really useful. You've probably seen these in school. If you haven't seen them quite yet, you will. 10 to the 1, that's a 1 with 1 0 after it. So if you ever see 10 to the 1, that's what it means. It just means 10. 10 to the 2 is a 1 with 2 zeros after it. So that's 100. And then you can imagine the pattern kind of goes up. 10 to the 3 is a 1 with 3 zeros after it. So that's 1,000. And it also has a prefix associated with it, which is kilo. So for instance, if someone had a gram mass, that'd be very small. Maybe the mass of like a paper clip. But if you wanted to scale that up, you could talk about kilograms. And that would be 1,000 of those grams. Same thing with meter and kilometer, right? A meter is about this big, A kilometer is 0.6 of a mile around. So a kilometer is 1,000 of these meters, right? And you can scale down to with centimeter and millimeter, stuff like that. 10 to the 6, 1 with 6 zeros after it. The prefix is mega. So, for all of you hopeful millionaires out there, maybe some of you play the lottery, maybe some of you aren't quite old enough yet, or maybe don't want to. But if you win the lottery, you become, you win the mega bucks, they say, right? Mega bucks, that's $1 million, right? So mega means million, 10 to the 6. Giga is another one. Think about hard drives. Although hard drives are actually becoming larger than gigabytes now, they're starting to go to terabytes and beyond. But gigabyte literally means 1 billion bytes of information can be stored in that hard drive. And so giga is 10 to the 9, a 1 with 9 zeros after it. So, okay, so, let's kind of, one thing that Roger and I would like the audience to kind of take away from today's talk is just how much energy does the country use? Just how much energy do we need for all of us, aside from just California, what about all of America, right? That spotlight that was on me earlier, that was a kilowatt of power. That's energy in use, right? So 1,000 watts of power is a kilowatt. And that's basically how much energy the average Californian uses in their home each day, okay? And so if you kind of scale that up, you can say, well, guess what? There's 350 million Americans out there. And Roger was pointing out, we do pretty good as Californians. We use kind of less energy than the average American. But let's just keep it kind of simple. If we were all using 1 kilowatt of power continuously as Americans, and there's 350 million Americans, then that means there's 350 million kilowatts of power that need to be generated. That's equivalent to 350,000 megawatts of power. And so the power plant that Roger showed in the last slide, that was a 300 megawatt power plant. But for the residential energy or power output, we need 300,000 of those. So that'd be equivalent of 1,000 more of those throughout the country to power our electricity needs in our homes. So that kind of gives you an idea of kind of how much power we need to produce.
Thanks, Dean. So as we build new plants, we have different choices. We can build them with wind. Last year in the United States, we built 2.2 gigawatts of wind power. So that's about 7 times bigger than that individual plant that I showed you. We can do it with solar. This is just utility scale solar. This is not the solar that many of us have on our rooftops. But again, last year, about 2.3 gigawatts of solar power was installed. Natural gas, like the plant that I showed you. A little more than 6 gigawatts of new natural gas plants were built. And now the big one that's missing is coal. Anybody care to hazard a guess of how many coal plants came online last year in the United States? 0. Not a 1. We're moving into an age where we don't need to use coal anymore because we have these new, cleaner sources of electricity. and this is good news for everybody. We're moving into a new age that interestingly comes from fracking. And it's changed the picture in the United States very dramatically. This is something that did not occur when I was a child. It didn't occur really at any scale of substance until about 7 years ago, when many of you were just in third grade. And it's changed the energy picture dramatically. It's changed the choices that we've made, and it's changed the choices that you're going to have to make into the future. One of the very first things that has changed is the choice between coal and natural gas. I told you that utilities like those natural gas plants because they're clean. It turns out they're actually inexpensive. They cost half as much as a coal-fired power plant to build. The biggest, from my viewpoint, is the climate impact. I'm a climate scientist. I care how much carbon dioxide goes up into the air. And it turns out that coal puts twice as much carbon dioxide into the atmosphere as natural gas to make the same amount of electricity. So to make a megawatt hour, 1,000, to power 1,000 of those spotlights that were on Dean, makes about 2,100 pounds, about a ton of carbon dioxide if you use coal. It only makes 1,000 pounds of carbon dioxide if you use natural gas. So from a climate standpoint, it's much better to use natural gas instead of coal, if you have enough of it to use. And that's a big if. This has had a major impact, though, on the energy, the climate impact of the United States. On the left-hand side, you see a graph of the amount of carbon dioxide that the United States has emitted since I was about in high school, since I was about in your age. And it's climbed and climbed and climbed and climbed. We emit more CO2 every year. We use more gas. We have more Xboxes. We have more TVs. We use more electricity. We emit more carbon dioxide. Then, about when you were in third grade, it turned over, started coming down. Why did it start coming down? Well, because we're using less fossil fuels, but let's look at where we're actually using them. Petroleum, what we use to run our cars. We're using less and less of that in the last 7 years. Why is that? Because our cars are more efficient. I call that the Prius effect. Good job. If you got here in a hybrid, you're contributing to that number coming down. Coal has been a huge change, though. Look at how much the emissions from coal have gone down over the last 7 years. And why is that? Because of the graph that I showed you of the new power plants. We're not building coal plants anymore. We're replacing them with these clean new energy sources, wind, solar, and natural gas. And you see the natural gas line is, in fact, turning up during that period because we're using it to replace coal. It only turns up half as much as the coal goes down because the carbon dioxide from natural gas is not as great as from coal. That's good for the whole country. We're doing a good job. Keep it up. But let's think about how each of us as an individual emits carbon dioxide. Dean, can you help us think about that?
Sure. Really, you want to think about two different energy needs out there, right? One of them is running electricity for your house, and one of them is the energy that you need for transportation. And in both those situations, you're basically accessing fossil fuels in many cases to basically burn them to get the energy that's locked into the chemical energy of a fossil fuel. When you burn fossil fuels, they release carbon dioxide, and as Roger was saying, that's a greenhouse gas, and that contributes to a warming planet and contributes to climate change. So we really need to be careful and think about how much carbon dioxide we're emitting into the atmosphere. I have some students from Tracy High that I'd like to call on out. And so this is a weather balloon that we filled up. And basically, this represents, if an American were to use a kilowatt of power continuously, that's the average American or California residential usage is 1 kilowatt of power. This is how much CO2, this is the volume of CO2 that would be released after 1 day. So it kind of shows you visually, okay, that's how much CO2 I've used to use that kilowatt of power, okay? Again, on the other side, we have transportation, right? And so we have a few more students that have another weather balloon, and this represents the amount of CO2 that burning 1 gallon of gasoline produces. This is just 1 gallon of gas. And it turns out the average American uses about 1 gallon of gasoline a day. Some people are commuting into San Francisco maybe, and they're using quite a bit more of that, but then some people aren't. So on average, Americans are using 1 gallon of gasoline a day. And so this is how much CO2 is coming from burning 1 gallon of gas. So, you think of the car driving around, and you have this like invisible emission coming out, but we wanted to kind of illustrate just how much CO2 kind of our daily activity is producing. And this is just 2 balloons, right? This would just represent 1 person in the room. Remember, there's 350 million Americans in our country. So that's the equivalent of 350 million of these balloons being produced for emissions on a daily basis. And that really gives you a visual of kind of just how much CO2 is really going into the atmosphere from our energy consumption. Okay? Well, let's give these students a round of applause. They did a great job. Thank you.
So we make carbon dioxide by burning fossil fuels. What are those fossil fuels and where do we get them from? We have petroleum that we turn into gasoline. We know about that. We have natural gas. I'm going to talk about that a lot more in the talk. And coal, which is the thing that we're trying to move away from because it's dirtier and emits more carbon dioxide. But these all come from very similar places. And I want to tell you a little story about where they come from. When I was a kid, I thought oil came from dinosaurs. Turns out it doesn't. It turns out it comes from the leaves that fall into the swamp that the dinosaurs were busy fighting over. As you all know from your homes last fall, there's a lot more leaves that fall into your yard than there are dinosaurs running around in your yard. The leaves build up over time, especially if they fall into water, if they fall into a swamp or if they fall into a shallow ocean. They get mixed in with mud from the water, and it forms a thing called a mudstone. That's going to last a long time, particularly if it's wet. Now, the next year, you get another layer, comes in, buries it. Next year, another layer buries that. Hundreds and thousands or even millions of years, you get millions of layers, and the layers get deeper and deeper. And we all know that when you go deeper in the earth, it gets hotter. And this has an interesting effect. It cooks those leaves. As it gets hotter, the leaves start to change into other chemicals. And that rate at which they change and what they turn into depends upon how hot they get. If they stay just a little bit warm and they stay that way for a long time, they turn into coal. And in fact, in coal, you can break open a piece of coal and you can still see the imprints of the leaves inside it. It hasn't changed very much at all. It's basically a bunch of leaves that have been compressed and cooked a little bit. If you leave them to cook at a higher temperature for a longer period of time, they turn into oil. They start to break down. You can't see leaves there anymore. And you have liquid oil that's present in the rock. If you get them to even higher temperature or cook them for the very longest period of time, which happens at very deepest levels in the earth, they cook and they turn into natural gas. You basically convert all the carbon that's in these rocks into natural gas. And that's good because you have a small amount of carbon in the rock compared to how much energy is there now, which is why natural gas emits less carbon dioxide than other fuels. It's interesting to think about these things, though. They come from leaves. They're basically solar power, right? I mean, the leaves absorb the sun and they're making turning into fuel, so why are we worried about fossil fuels different than solar power today? The problem is we're using them so fast. We're using them so much faster than these poor dinosaurs could make them. I'm sorry, they're not dinosaurs making the fuel, are they? They're really leaves. But anyway, the point is we're using them so much faster than they were made that we're using up this supply that was stored maybe 100 million years ago, which is when many of these fuels came from. Now, how do we get them out? This is a picture from the La Brea tar pits, which I bet some of you had visited. The oil and the leaves that it came from, visible in the same picture, like that. Oil is lighter than water, and at La Brea, it'll bubble up out of the ground as it basically floats on top of the water. But that's not usually the case. Usually, we have to work a lot harder to get oil and gas out of the ground. And I'll show you what a conventional oil and gas reservoir looks like. It looks a lot like beach sand, only it's turned into a rock. It's turned into a rock called sandstone. On the left, you see that sandstone. There's still spaces in between the sand grains. And you know when you go on the beach and a wave washes up on the beach and it fills the beach with water, and then the wave goes back and the water runs back out of the sand grains? The same thing can happen inside the sandstone that oil and gas accumulate in. The spaces between the sand can fill with oil or fill with gas. And if you have a trap, if you have like an inverted coffee cup in the ground, if you have the rocks are bent in such a way that they trap that oil and gas into one localized place, that's an oil reservoir. And all you have to do to get that oil out is drill a hole into it, put a straw in it, and suck it out. Well, I don't recommend that. Put a pipe into it, pump it out. But it's pretty easy to get out, and the oil comes out from between those sand grains. And that's what almost all oil and gas production, up until the point that you were in the third grade, came from. And then we started developing it from a new resource called shale. Well, what's a shale? Shale's the same thing. We still have the same leaves falling in the same swamp, only now there's more dirt that mixes in with them, and it forms into a really, really tight rock. Shales are not permeable. Remember the beach sand that we talked about, the water would flow in and out of it. But a shale, water will not flow through it. It's impermeable. It's about as permeable as the shingles on your roof. Not much water flows through there, right? So when the leaves get caught in there and they get cooked, what happens to oil and gas? It stays there. It never gets to migrate out and form this thing that you can suck out with a pipe. So the oil and gas has been sitting there for 100 million years, and there's no way to get it out unless you break up the rock, unless you fracture the rock, and this is where that word fracking comes from. So there's an enormous amount stored in these, but we haven't been able to get it out up until this point. But it's all over the country. And this is a map of where some of the main shale gas resources are around the country. You'll see the Marcellus there in Pennsylvania. You'll see the Bakken in North Dakota. Who knows that North Dakota is now the second largest oil producer in the country. Surpassed California, went way past us, and it was almost caught up to Texas, except Texas also has shale gas in it, so it's also going faster. These shale deposits are distributed around the country. The interesting thing is that because of some of the shales back east, that's where most of the people live, and so the natural gas no longer has to be piped all the way across the country. They can actually produce the natural gas near people's homes where it's actually being used. The amount there is impressive. Just in these 7 places, there's enough natural gas to fuel all the natural gas needs of our country for the next 30 years. Now, that might not sound like too much, but to a utility executive who wants to build one of those power plants, when you were born, we only had 2 to 5 years of natural gas in the bank, so to speak, that we knew about. And so they would say, I'm not going to build a natural gas-fired power plant because I'm not sure I'll have gas to run it on. Now we say we have 30 years worth, and not only do we have 30 years, but these are just 7 of the 43 shale deposits that are in this country. There's an enormous amount out there, and so people are much more confident that they can use this nice, clean natural gas, and they're not going to run out of it before their power plant is done working. But how do we get it out? It's hard to get out, as I said. It's an impermeable rock. So I'll walk you through how we do this. First thing is you have to drill a well. Drill a well very deep. These digs are typically 7,000 to 10,000 feet deep, 2 miles deep. That's from here to Granada High School, drilled straight underneath your feet. And in the early 80s, when I first started working at Lawrence Livermore Lab, the country figured out how to do something else that was really remarkable. Drill that well straight down and then turn it sideways and drill it horizontally. So now we could drill into these tight rocks and follow them underground. They can keep one of those drill bits inside a small room. They can keep it inside your bedroom for 2 miles. They can control it so tightly. It's amazing to me that they can do that. But even just drilling a well into this rock doesn't get the oil and gas out of it. You drill the well in and not much happens. You have to fracture the rock in order to get more out of it. Now, how do we do that? The way we do it, first of all, is the fun part, is the well is a pipe, right? It's a steel pipe. So you have to have holes in that pipe, and so there's a little tool called a gun, and it's loaded with things that are essentially great big shotgun shells, and you put that in the pipe, and those shotgun shells punch holes in the pipe. They shoot holes in the pipe, and now you can pump things through those holes. And what you pump through those holes is water. You pump water at very high pressure, and it cracks the rock, fractures the rock, and that's the actual fracking process. Now, the rock is deep underground. If you just fractured it and then you walked away, it would close up again because it's got all this rock pushing on it. But you inject sand along with that water, and the sand keeps it open, basically makes it act like that sandstone that I was telling you about, a conventional oil reservoir. So now instead of finding an oil reservoir, we're creating an oil reservoir by fracturing it. You use an enormous amount of water to do this, but you have to get that water back out of the way because you want to get oil and gas out, so you have to pump that water back out of the well. The way you pump the water in, though, is very interesting. You imagine you getting enough pressure to fracture a rock, you must have to use a lot of pressure, right? So I was visiting one of the companies that makes this kind of equipment, and they said, would you like to see our factory where we make these pumps? They call them frac pumps. I said, of course I want to see that. And they took us out back, and there's a great big long shed, and they have tractor trailers pulled in from either side, and they're loading equipment on. They said, first we start with the biggest tractor trailer that's legal where we're going to use it. And then we take the diesel engine, the same diesel engine that's used in a locomotive, and we drop that engine down on the trailer. And of course, it covers the entire length of the trailer. And we put a pump on the back side of that. The pump's only about this big. It's only about 5 feet across to pump the water. And I say, oh, okay, so that's a frac pump. They said, no. You put 20 of those together. That's a frac pump. 20 diesel locomotives required to actually fracture the rock. This is one of the reasons that this technology has been successful in the United States and not so much elsewhere yet, is because we have the infrastructure, we have the people, we have the machinists, we have the guys who know how to do this stuff. We can build these things, these enormous amounts of equipment that need to be done to do this. But another question you might ask yourself about a process like this is, how do we know what's happening underground? You can't crawl down there and look at it. It's 10,000 feet underground. The fractures are only about 1 centimeter across. You can't even send a camera in to see what they look like. This is something we work on in the lab. We want to understand where those fractures are. We want to know that they go where you want them to be. And so we use computer modeling to study this. And this is a model built by a friend of mine named Peng-Cheng Fu. And these are fractures you've seen that would really look like in a developing shale gas field like you saw in the Marcellus in Pennsylvania. The fractures open up as the water pumps into them. I've overemphasized how much they open up here so you see them. They're really only 1 centimeter, and the scale of this entire picture is 1 kilometer, remember. But one of the things that's interesting about this is that there's only really 2 children in this family that do really well, that get extra dessert, the 2 on the ends. And everybody in between gets squeezed by the other 2. Some of you may be familiar with that problem. The fractures in the middle are not as good as the fractures on either end because they're getting squeezed, and it's hard to break the rock open because it's being squeezed on the outside. You wouldn't know this if you didn't have computer models to do it, and that's one of the things that we do at the laboratory. We use that to see the unseen. We've talked about natural gas a lot. I'm a climate scientist. Natural gas really matters to me because it helps us replace coal. It helps us have clean electricity. It helps us to do so with as minimal a climate impact as we can get today. But the big story as far as the US goes is petroleum, is oil. I'll walk you through the history of oil in this country a little bit. Back before World War II, we used about as much oil as we produced. And after World War II, things changed. We started consuming more oil than we produced. That line started going up. And where we were getting that oil, we were buying it from overseas. And during the 70s, we had some terrible crises where basically what happened is the people overseas said, you're not paying us enough. We're going to stop giving you oil. It caused shocks. It caused it caused lines to get gasoline around here. It caused dramatic changes in our political thought process around that because we all like our cars. We wanted to have the gasoline to run our cars. The other thing that happened about the same time in the United States was we reached our peak production. We'd been producing more and more oil every year. Suddenly, we were producing less oil every year. So now we got ourselves into a bad situation. We were buying a lot of oil from overseas. We were producing less. And the other thing we were doing, this was really smart back in those days, we were using oil to make electricity with it. And that's why you see those spikes every year in the consumption graph. You make more electricity in the winter than in the summer, and so that you'd spike it. Well, fortunately, we figured out we shouldn't use our petroleum to do that. But for the next 30 years, this was a story. Every year, we used more oil. Every year, we produced less. This is the environment that every policymaker, every politician, people my age, this is where we grew up in, and this is how we thought about energy. It was all about this. Every year, it got worse. Every year, we had more trouble. It's not happening anymore. Since you were in 3rd grade, every year, it gets better. It's a new age of abundance. It's a remarkable thing. First thing I want to point out, because you've had something to do with it, is we're using less oil every year. It's because of the Prius effect. We're using more efficiently, we're using less, and we're getting more value out of the oil that we use. But the purple line down on the bottom shows you that we're producing an enormous amount more oil in this country, and that's coming from fracking. In fact, sometime this year, we're going to produce more oil in this country than we ever have before. We're going to surpass that number in 1970. And this results in an entirely new game of musical chairs. It used to be that every year a chair got taken away and somebody had to do without. This year now the musical chairs game is every year there's an extra chair. And that's a much more fun game, isn't it? The money has been a big deal, though. 7 years ago, when you were in 3rd grade, we were buying 16 million barrels of oil from overseas sources and paying them $100 a barrel for that money. This year, we're going to buy 10 million barrels of oil. It's still a lot, but it's a lot less. And that difference, $100 a barrel, is $600 million a day that we're no longer sending overseas. We're still buying a lot of oil. We're using a little less, but we're buying that oil from American sources. We're spending that money in the United States, and that has a huge impact on our economy. And if you wonder why politicians seem to be in favor of fracking in general, that's the reason. It has a gigantic economic effect. But it's not for free, is it? There's giant environmental consequences that go along with the giant economic consequences. And this is what we want to close out the talk talking about. Do we trust this age of abundance in the hands of big oil? Not many of us do. And I think that's one of the fundamental problems we have, is we have something that's really remarkable in this country, and who's in charge of it? Well, a group that we really don't fundamentally trust. And this has led to a lot of concerns. But I want to talk about the sort of direct environmental concerns that we see when you're doing fracking, and what you all can do to think about solving these problems. First one I want to start with is really kind of a simple one, truck traffic. It takes 1,000 truck trips to build one of those wells that I showed you. They have to deliver sand, they have to deliver water, they have to deliver drill pipe, they have to deliver the chemicals that get used underneath. 1,000 truck trips in rural Pennsylvania, that picture that I showed you there in the Marcellus, that's a lot of trucks on something that's used to seeing a pickup truck a day. The impacts are gigantic. And what if one of those trucks happens to spill its load into the local creek? The environmental consequences are tremendous. So just traffic is important. When the state of Pennsylvania started, the fracking boom started in Pennsylvania, they were not taking account of this. Today, if you want to apply for a permit to drill a well in Pennsylvania, you have to pay them $50,000 just to submit the paperwork. You get nothing for that. And they take that $50,000, they're spending it on better roads and inspectors and things to control this kind of thing. But it's a simple thing, but it has a gigantic impact when you talk about industry on this scale. But the big thing is water. This has always been the flagship issue. And the problem here is that you use a lot of water, and that water looks like the water that you see on the left. What is it? It looks like whale snot to me. It's water with guar gum in it. What's guar gum? That's the same thing that thickens your McDonald's milkshake. Think about that the next time you're in line. It's exactly the same thing. In fact, for a while in the beginning of the fracking boom, McDonald's was complaining they couldn't get enough guar gum to make their milkshakes because the frackers were taking it all. So if I was up here trying to sell you guys that fracking was a good idea, I'd say, oh, look at it, it's mostly water, 99.51% of it's water. Well, that's not the whole story. There's important things that you have to mix into that water. One of them is guar gum, which is the gelling agent. But there's other things in there. There's acids, there's friction reducers, and surfactants. What are those? Soap. Okay, that's things to make the water slide down all that pipe and go into those little thin fractures. Remember, those fractures are only a centimeter wide. There's a lot of friction in pumping water into them at high pressure. Some salt, potassium chloride. It's like sodium chloride that's in your salt shaker at home. What's that there for? That's to keep the water from interacting with the rock too much. And then up at the top, though, are some important things. Scale inhibitor, biocide. What's a biocide? It's something that kills anything biological. Bleach is a biocide. The biocides they're using here are actually more potent than bleach, but you can think about it that way. And these are important because when you inject things underground, there's always bacteria. They're going to grow. If those bacteria grow inside your well, they can clog your well. So they use a biocide to keep it from growing. Well, gee, we don't want this biocide coming out and getting into our drinking water, do we? That's a big deal. You want to make sure you manage that. And this list of chemicals that are put into wells, typically there's about 100 chemicals that go into each fracking well. One of the debates that's been going on is some of the companies say, we don't want to tell you what's in our magic formula because it's proprietary so we can do our best possible job. And that's just wrong. I mean, this is important to all of us. In the state of California today, if you want to frack a well, you have to tell the state every single chemical that you're using by name. And that just makes sense. Of course, we want to know what's in there, because then that helps us make up the regulations and control things so that these things get safely managed. Because obviously, it's not just water. There's important things you have to do there. What comes out is kind of interesting. Why does water come out again? Well, you've got to pump the water out of the well so you can get the oil and gas out of the well, right? Or it's in the way. And on the right-hand side, you see what the water looks like as it comes out. It's a mess. Why is it a mess? Because it's breaking down as it comes out of the well. You're breaking down this guar gum so you can pump it out. If you didn't break down the guar gum, it wouldn't move, so you have to put in something to break that down. And then you have all these other chemicals that come out. So what do you think the average company wants to do with this when they get it out of the well and it looks like that mess? They just want to throw it away because they don't want to take the time or spend the money to clean it up. And that's a mistake. In Canada today, in their fracked wells, every single drop of water gets recycled. They take that water, they clean the chemicals out of it, they reuse the water. Makes a lot of sense. It costs penny per gallon. This is the sort of thing that we're moving to in the United States, but it's the sort of thing that we need to really make sure that companies do the right thing and treat this water appropriately. Because what happens when they throw it away? Fortunately, they don't throw it away in surf. They don't dump it into streams or something. But one thing they do tend to do with it is pump it back deep underground. And in this case, they just keep pumping and pumping and pumping and pumping, unlike the frack well where they pump until a fracture breaks and the fracture moves about the size of this auditorium. It's about 100 feet or maybe 200 feet. And then they stop and they'll move on to another fracture, make another fracture. But when they're disposing of the water, they just keep pumping it day and night, day and night, day and night. And what do you think happens from that? Causes earthquakes. State of Oklahoma now had more earthquakes in 2014 than California did. That's wrong. That's coming because they're causing the earthquakes by disposing of this water that doesn't need to be disposed of because it could just be cleaned up. This is the kind of choice that we all need to make, and that we all, if we're going to use the abundance of shale gas, we need to manage the environmental concerns as well. Last thing I want to talk about is kind of an interesting one. Natural gas is itself a greenhouse gas. It's a potent greenhouse gas. In fact, it's 25 times stronger a greenhouse gas than is carbon dioxide. And if we were to let that leak into the atmosphere, it doesn't matter if we're being twice as good as coal, if we're 25 times worse because we're letting the methane leak into the atmosphere, letting the natural gas leak into the atmosphere. So we have to be very careful not to let it leak. This is something that's poorly understood at this point. This is something that many of you in this room are going to study, you're going to work on in the courses of your scientific careers. Because I know you're all going to be scientists. You all look like you're really excited about it. Controlling this methane today is done by flaring it off. If you don't have a pipeline to put it into, you're going to burn it. So what are we looking at in this map? What are these lights that we're seeing? You see Chicago and Minneapolis. Those are the lights at night from the cities, from the street lights in those cities. And what's that blue one out? It's labeled the Bakken Formation. That's out in North Dakota. There's no cities in North Dakota. There are so many wells out there, which there's no pipelines to, that they're just burning off the natural gas to the extent that you can see it from space at night. Well, that's a waste of resources. We need to get the pipelines there so we can do that. And they're running the pipelines. They're getting them there. That problem is being solved as we speak. It hasn't been not done yet. But it points out a really important thing here, that we need to manage where the natural gas is going, whether it's leaking. Turns out people have done studies and found that, for instance, the city of Boston is leaking an enormous amount of natural gas from its old pipelines. It has a big climate effect. We have to, if we're going to be using natural gas in the future, we're going to use it for a big part of our energy picture, we have to manage the environmental impacts of that as well. And this is one of the things that's going to be an important part of your lives. And here's the challenge for you. You live in an age of abundance. It's a new age of abundance. It's something that policymakers, the guys with the gray hair, we don't know about this because it's new. It's for you guys to figure out. And it's an energy abundance, but it's also a gigantic environmental challenge. Natural gas is letting us move beyond coal. It's letting us put coal behind us. It's making the country a lot of money, and that's good for everybody. But it's also creating a gigantic environmental challenge. We want to burn the oil. If we burn the oil, then it's going to turn into carbon dioxide. We want to produce the oil, and we have all those environmental issues associated with fracking and making it. So we have to balance all those things. You guys in the room are going to have to balance the choices of how you do environmental and energy choices as you move forward. The good news is we now have many more ways to succeed than we did when you were in the third grade. It's a much better picture. It's better to deal with abundance than to deal with scarcity. We have choices that we can make. We have new engineering, new science that we can apply to these. And these are the kind of things, this is going to be the great endeavor of your age. These are going to be things that you're working on, and I know you're going to make very good choices. And Dean, why don't we talk to him about those choices?
Okay. So you've been hearing a lot of things about natural gas, about fracking, about the benefits to it, and also the consequences of accessing natural gas. So, we have some decisions to make, and we have an opinion poll that we'd like to have you participate in. This is a Science on Saturday first, and actually, since you're the second show, it's a Science on Saturday second. What we learned from the first show is we actually can only get the poll data from the first 40 people to participate. So it's actually kind of a text race, and I hope you're ready to participate in a text message race. So remember, text messaging rates apply. You should have permission from your parents before you text. So to participate in this poll, you have to text a message to 37607. That's the number you're going to text to. And the message that you're going to send is Dean Reese 259. So you're going to text to the number 37607, the message Dean Reese 259. And once you do that, you'll be in the poll. Okay? And you can begin now. Once you're in the poll, you're either going to basically send a text message of A, B, or C once you're in. And then we'll get some data from you guys about whether or not you think fracking is a temporary solution to our energy issues in the country, our energy demand in the country. Do you think fracking for natural gas is a permanent solution? It's something that you're saying, you know what, this seems great, let's do it. Or do you think fracking for natural gas just simply is not a solution after what you heard today? And there's no right answer to this question. This is just an opinion, and it's going to be a different answer for everybody. So we kind of want to see what you might think. So we have room for 40. So right now we have about 12 of you in the poll. We'll let it run for a little while longer before we kind of see what you think. You're texting Dean Reese 259 to the phone number 37607. That'll get you in the poll. And once you're in the poll, choose either A, B, or C, depending on what you think is your answer.
Well, of course,
there we go.
It's rather thinly veiled. What we're trying to do is get you guys to think about these questions and think about what choices you would make in the future and hopefully what careers you would pursue in the future. Because there's a lot of science, a lot of engineering to be done, and you guys are going to be the ones to do it, and it's going to be an exciting time. It's going to be a lot of really good things to do, and good news is there's going to be the money to do it with. Thank you very much.